Myself, Madhus, Assistant Professor of Physics, Government First Grade College, Srinivaspur. I would like to discuss on the topic scalar and vector fields, paper 301, Electricity and Magnetism for BSc Physics, 3rd Sem, Bangalore North University, session number 32. Learning objectives from this topic to understand the divergence of a vector field and curl of a vector field, physical significance of divergence of a vector field and curl of a vector field. Course learning outcome from this topic, ability to understand regarding the concept of divergence of a vector field and curl of a vector field. Physical significance of divergence of a vector A and curl of a vector A. From this slide, before going into detail, illustration regarding divergence of a vector field at point P. If a point P, if a vector field expansion from the source field takes, then the divergence of a vector field is positive. If a vector field making contraction, or if a vector field acts as a sink, then negative divergence. If a vector field entering and leaving same, then divergence of a vector field is 0. Let us discuss divergence of a vector field. Divergence of a vector field is vector operator that operates on a vector field producing scalar field giving the quantity of the vector field source at each point. Divergence of a vector field means spreading or diverging of a quantity from a point in a field. Divergence of a vector field can be written as del dot A. In previous session, we have understood del can be written as I cap dou by dou x plus j cap dou by dou y plus k cap dou by dou z, where vector A with respect to x, y, z coordinates with respect to unit vectors I cap, j cap, k cap can be written as I cap A of x plus j cap A of y plus k cap A of z. If we multiply with respect to dot product or scalar product, then the product output can be written as divergence of vector A equal to del dot A equal to dou A of x by dou x plus dou of ay by dou y plus dou of A of z by dou z. Next we shall discuss and to prove dv, divergence of a vector A equal to dou of x by dou x, dou of ay by dou y plus dou of az by dou z. We can prove by using parallelepiped. Let us discuss by considering parallelepiped. Consider a parallelepiped in which velocity of a fluid entering and leaving from the phase P, Q, R, S, E, F, G, H, dz and dy and dz, dx along x-axis, whereas dy parallel to y-axis, dz along z-axis. Next, the value of a of x at the center M of the phase P, Q, R, S equal to value of Ax at center plus increase in magnitude from C to M equal to value of A of x at center plus rate of change of vector A of x with respect to x-axis into distance from C to M can be written as d of x by 2. C of M is having distance of dx from n to n dx. Therefore, in place of distance from C to M is dx by 2. Therefore, value of E of x at center E of x plus rate of change of vector A of x can be written as dou of Ax by dou x dot in place of distance d of x by 2. Therefore, A of x plus half of dou of Ax by dou x into dx. Similarly, on the phase EFGH equal to A of x minus half of dou of A of x by dou x into dx. Here negative sign indicates point N, which is left side with respect to the center C, whereas point M is towards right side to the center of parallelepiped. Therefore, area of a phase EFGH equal to dy into dz. Flux definition we know: magnitude of vector entering to the phase EFGH, product of area. Magnitude at center of the phase EFGH value we know. Therefore, into area is considered as flux entering to the phase EFGH can be written this. Similarly, flux entering to the phase PQRS can be written as A of x plus half of dou A of x by dou x into dx into dy dz. The excess of a flux leaving from the parallelepiped over that entering in the x direction can be written in this type. In this case, plus Ax minus Ax cancels, remaining half of dou Ax by dou x dx dy dy plus minus into minus plus half 1 dou Ax by dou x dx dy dz. These values indicates flux leaving, excess flux leaving from the parallelepiped over entering along x direction. Similarly, along y direction, dou y dou ay by dou y into dx dy dz. For z direction, dou az by dou z into dx dy dz. Adding all the flux leaving along x, y and z, then dou az by dou z into dx dy dz, taking common dx dy dz, where dx dy dz represents volume of the parallelepiped. Therefore, divergence of A, excess flux per unit volume, excess flux per unit volume with respect to x, y, z direction will be equal to dou A of x by dou x plus dou A of y by dou y plus dou A of z by dou z. Divergence of a vector field can be positive divergence and for negative divergence or zero divergence. Therefore, divergence can be non-zero, divergence can be zero. At a point P, vector field expansion takes place from a source, then the divergence of vector A will be positive. If a vector field is converging, then divergence of vector A is negative and then is sinks. Divergence value is 0 if a vector field entering and leaving element same, then divergence can become 0. Next, curl of a vector field is defined as maximum line integral of vector per unit area, which can be represented as curl of a vector A equal to del cross vector A. Meanwhile, divergence of vector A can be written as del dot A. Difference between divergence of a vector A and curl of a vector A. For divergence, del dot vector A. For curl of vector A, del cross vector A. Therefore, it can be written in the determinant form I cap, j cap, k cap, dou by dou x, dou by dou y, dou by dou z, a of x, a of y, a of z. To know the first term, we should have to take and we should have to neglect these terms. To know the I cap component, if we differentiate dou of az by dou y minus dou of ay by dou z. Similarly, from this determinant rule, we can find easily I cap component, j cap component and k cap component. Consider small rectangular surface A, B, C, D. P be the center of rectangular surface. ds be the length along x-axis, dy be the length along y-axis. Let us consider point Q, R, S, T. Next, vector field A, whose component along x-axis can be represented by A of x, along y direction A of y. Rectangular of a vector field subjected in space of vector field, then rate of change of vector A of x along y-axis can be represented dou of A of x by dou y. Dou of ay by dou x is the rate of change of A of y along x-axis. The increase in magnitude of A of x going from P to R. P to R dou A of x by dou y. P of R equal to dou A of x by dou y, half of dy equal to half of dou A of x by dou y into dy. Thus the value of A of x are equal to A of x plus half of dou A of x by dou y into dy acting along RC. Similarly, the value of A of x at t equal to A of x minus half of dou A of x by dou y dy acting along TB. The value of A of y at q equal to A of y plus half of dou A of y by dou x dx acting along QC. The value of A of y at S equal to A of y minus half of dou A of y by dou x into dx acting along SD. The line integral along the boundary A, B, C, D equal to AB into component of vector AB plus BC into component of vector BC, CD into component of vector CD, DA into component of vector along DA equal to AX minus half dou A of x by dou y dy dx. Similarly, component of vector BC into BC. BC is nothing but dy. For component of vector along CD, component along vector dA. Line integral along the boundary ABCD gives rise to dou ay by dou x minus dou A of x by dou y into dx dy. Line integral per unit area dx dy cross multiplication. Line integral per unit area equal to dou ay by dou x minus dou ax by dou y. Therefore, line integral per unit area can be represented as curl along z direction equal to dou ay by dou x minus dou ax by dou y with respect to unit vector A. Similarly, curl A along y and x can be written as curl A of y equal to dou ax by dou z minus dou A of z by dou x with unit vector j cap. For curl A of x equal to dou A of z by dou y minus dou of ay by dou z into I cap. Sum of curl along x plus y and z. Therefore, curl A equal to dou az by dou y minus dou ay by dou z I cap plus dou ax by dou z minus dou az by dou x j cap plus dou ay by dou x minus dou A of x by dou y into k cap. This equation can also be expressed in different form of curl vector A equal to del cross vector A can be represented in determinant form. To know the I cap component, we have to cross multiply dou az by dou y minus dou ay by dou z. Next, to get this value, we have to neglect along vertical as well as column row we have to neglect. To get this value, we have to cross multiply this as well as this. Dou az by dou x minus dou a of x by dou z. Similarly, to get this component, we have to neglect x as well as vertical row column as well as row. To get this value by cross multiplication, first dou ay by dou x minus dou ax by dou y into k cap. Physical significance of a curl vector is concerned with respect to rotation of a vector field. Curl of a vector field represents 0. There is no rotation. For example, uniform magnetic field exposed for a rectangular surface, then curl is 0. Whereas current carrying conductor experiences non-uniform magnetic field around the conductor. In this case, vector field is rotating, which represents curl is non-zero. For this condition, curl is 0. If a field is uniform, then curl of a vector A is 0. If a field is non-uniform, then curl is non-zero. From this session, we have understood the concept of a divergence of a vector field and curl of a vector field, physical significance of divergence A and curl of A. Now let us discuss multiple choice questions on the topic. First one, divergence of a vector is a scalar. Option A, true. Option B, false. Option C, both. Option D, none of the above. Answer is true. Option A, divergence of a vector is a scalar. Vector del dot A is always a scalar. Next question, find the divergence of a vector. Del dot A equal to y del dot yi cap plus zj cap plus xk cap. If we differentiate with respect to x, y is constant, z and x. If we differentiate with respect to x, then the value will be 1. Whereas variable is different, therefore according to the answer, option A is -1, option B is 2, option C is 0, option D is 3. Option C is the correct answer. Option C value is 0. Divergence of vector. If we diverge for this vector, answer is 0. Next question. Identify the nature of the field. If is 0. Option E solenoid. Option B rotational. Option C solenoid. Option D irrotational. Option D is irrotational. Answer. Fourth question. If a field in which test charge around any closed path is 0, option A is solenoid, option B is conservative, option C is irrotational, option D is rotational. Answer is option B, conservative. Curl of a vector gives a vector scalar 0 value and non-zero value. Curl of a vector gives vector. Option Option A. References